Hello, and welcome to the third and final video for the FP1 chapter Matrices. Start a question on the screen for you. Show that a squared equals I, where of course I is the identity matrix, and because this is a 2 by 2 that we're going to square, this will be I2, the 2 by 2 identity matrix. A quick note here, a squared of course is a times a, where the order doesn't matter because it's the same matrix. If it was a b squared, however, you've got to be careful that this is ab times ab, not a squared times b squared, which would be a different order. So here we need to show that a times a, which is 2 minus 1, 3 minus 2 times by itself, is going to give us the identity matrix. To show this, we just go ahead and do the multiplication. Here we have 4 minus 3. 4 minus 3, I'm just going to write like that for now. Minus 2 plus 2. Second row, first column is 6 minus 6. And second row, second column, minus 3 plus 4. Now I've written the calculations in there because if they're telling us this equals I could very easily just write 1, 1, 0, 0 without doing the calculation. This step, I think, in this particular case, is the show step. So showing what we've done to get these answers, this I can now see is a 1, a 0, a 0, and a 1, which is, of course, I2, the identity matrix. In this video, we are going to do two things. We're going to look at the determinant of a 2 by 2 matrix and find the inverse of a 2 by 2 matrix where it exists. We're going to do the two together because this is a big part of doing this. So the determinant of a square matrix is a necessary part of finding its inverse matrix, and determines if the inverse even exists. This is where the word comes from. It determines if the inverse exists, but we won't do that just yet. We'll come back to that in a few minutes. The determinant of a 2 by 2 matrix, M, if M is this, A, B, C, D, then the determinant is given by the formula A times D minus B times C. What I like to do here is draw a little fish symbol in my mind. I go from the top left down to the bottom left. And there's my little fish. And that helps me to remember. And what I do is I say A times D minus B times C. That might seem a bit silly, but if it helps you, you can do the same. And that's it. This is why I'm putting two sections together in this video, because for the determinant, so long as you can remember this, that's it done. A quick example here. Given that A is this 2 by 2 matrix, find, this is another way of writing it, the determinant of A. So for notation, let me write determinant of A, that's the same as this, and that is the same as putting the matrix elements in two big straight lines, like this. All of these mean the same thing. They mean do this element times this element, minus 20, minus this element times this element, which is 6. So in this case, the determinant of A is minus 26. And without talking about the inverse, there's no clear reason why we should care about that. So here is the inverse. The inverse of a square matrix, M, if the inverse exists, is written as m to the minus 1, and satisfies this equation here, that the matrix times by its own inverse gives you the identity matrix, or the inverse times by the matrix. So the order here doesn't matter. Both situations will give you the identity matrix. If it does, then the pair of matrices is a matrix and its inverse. And let me just give a quick bit of background here. This is similar to the idea that 7 times by the inverse of 7 is equal to 1. This is a comparable statement. The obvious difference is that when you do the inverse of 7, that's just 1 over 7, that's quite easy, whereas when you do the inverse of a matrix, it's not as straightforward as that. So here is the formula, and it is simply a case of remembering the formula by either memorizing it outright or by practicing it so much that it gets ingrained in your brain. So the inverse of a 2 by 2 matrix, I'm putting this here specifically because it's different for a 3 by 3 matrix. That's a much more complicated process that we will go through in FP3 if you do that module. So the 2 by 2 matrix, the inverse of this is given by the formula 1 divided by the determinant, that's why that's important, times by this matrix, where this closely relates to this one. And you swap the A and D elements, and you put a negative in front of the B and C elements, which of course, if they are already negative, turns them to positive. So this is a key thing to remember. It also explains why the determinant of M is so important in finding whether or not the inverse exists, because if the determinant of M is equal to 0, you're trying to divide by 0, you can't do that, which means the inverse of that matrix does not exist, and it is said to be singular. So singular is the word we use for this statement here. If it doesn't equal 0, then it's fine, you can find the inverse, it does exist, and it's non-singular. So here are a couple of examples. If possible, find the inverse matrix for this matrix and for this matrix. So I've got the two formulas up here, the determinant is this, the inverse is this. So let's do A first. If A is this, then the determinant of A is 4 times 3 minus 2 times 1, so that's 12 minus 2, which is 10. That is not 0, so the inverse does exist. So let's find the inverse of A. 1 divided by the determinant of A, that's 10, times by the matrix D minus B minus C A. So my A and my D elements switch places. So I put the 3 here and the 4 here. And then the B and C stay where they are, but I negate them. So we've got minus 2 and a minus 1. And if this fraction in front is not too terrible, you can always choose, if you like, to put that into the matrix. So here we could have this. Sometimes if the fraction is really horrible, you would opt not to put it into the matrix. And that's the first one done. The second one, B, is equal to 6293. The determinant of B is equal to 6 times 3, 18, minus 2 times 9, 18. And here we have a singular matrix, because the determinant is 0. We can't divide by 0, so there is no inverse matrix. That's another way of saying that if I wanted to multiply B by something to get the identity matrix, there simply is no matrix where this will work, because this one here, the inverse of B, does not exist. B is singular. And in terms of finding the inverse of a matrix, that's it. It's as simple as remembering these formulas and following the pattern. At this level, you will only need to do a 2 by 2 matrix, no other kind of matrix. But there is still an extra bit to this chapter, and that is a little bit of matrix algebra. Knowing that a matrix times its own inverse gives the identity matrix, and knowing a second bit of information, that the identity matrix times any matrix has no effect. It's like multiplying by 1. And this is another situation where the order doesn't matter. So this and this are powerful tools for some matrix algebra. But you must be careful to apply any multiplication on the same side of the expression for both sides of the equation. and I'll explain what I mean as I go through an example. So I'm going to use this result given in the book in one of the examples to go through and show what I mean. And this relies on A and B being non-singular matrices because, of course, if they're singular matrices, then these don't exist. So I want to prove this result here. To do that, I'm going to start with the statement that C times its own inverse gives us the identity matrix, where C is going to stand for the multiplication AB. And the very first thing I'm going to do is to put that in for C here. I'm going to leave the inverse of C because we're not entirely sure what that is yet. Well, we do know what it is. It's here, but we're trying to prove that, so we can't use the result in the proof. And then this is what I'm going to do. I'm going to multiply on the left of this expression by the inverse matrix of A. That means on the other side I have to do the same. I have to multiply on the left of this expression by the inverse of A. This is what I mean when I say it must be the same side of the expression on both sides of the equation. Because the order is so important in matrix multiplication, if I want to put the inverse of A on the far left of this expression, it must go on the far left of this expression as well. Now we're going to use again the fact that the inverse times by a matrix is equal to the identity matrix, and replace on the left here this by an I. So this becomes I, B inverse of C, and on this side I'm going to use the fact that the identity matrix multiplied by anything doesn't change that matrix. It's like multiplying by 1, as I said earlier. I'm going to do the same on this side. I'm going to say I times B is still just B, which gives me this statement. And then basically I'm going to do the same thing with B. I'm going to multiply on both sides on the left of the expression by the inverse matrix of B. And so long as I do that on both sides on the left, then this is still true. Now I can see that I have a matrix multiplied by its own inverse. I apply this rule again. That gives me the identity matrix. And then I apply the other rule, that the identity matrix has no effect on a matrix when you multiply. It's like multiplying by 1 to give me C minus 1. The inverse of C is equal to the inverse of B times the inverse of A. And now I replace C here with AB to get the final result. The inverse of AB is equal to the inverse of B times the inverse of A, where the order is very important. So the fact that A is first here and B is first here, that's important. So the two key things that allowed us to do this: a matrix times by its own inverse is equal to the identity matrix, and the identity matrix has no effect on a matrix when you multiply it. Important things to remember if you're going to answer any questions on matrix algebra. Here is another example. A and B are non-singular 2x2 matrices such that AB is equal to the identity matrix. Prove that A equals inverse B times inverse B. This statement here, given that we don't know what A is and we don't know what B is until part B, is all about matrix algebra. It's not always easy to know where to start, but in this case I'm going to start with what they've given me here and see if I can isolate A. So we have B is equal to I. If I multiply on the left of both of these expressions by the inverse B, then on the right hand side, an identity matrix multiplied by a matrix has no effect, and on the left hand side, the inverse of a matrix times by itself gives us the identity matrix, which in turn has no effect. Now I multiply on the right of both of these by the inverse of B, Not quite so obvious that I'm doing it on the right here because these are the same, but if these weren't the same, it would be very important that this is the new one that I've put here. And of course, b times the inverse of b, as we've seen, gives us I, and a times I is just a. And it's not unusual for questions like this to then ask you to do something with the result you found. Given that b is this, find the matrix A. In order to do this, I am using this fact here, so I need to find the inverse of b and then multiply it by itself, and that will give me A. So finding the inverse of b, I need to find the determinant of b first. That, my little fish here, gives me 6 minus 5. A very nice number because it means I won't have any fractions in my inverse matrix. 1 over the determinant, which is 1. 3 and 2 swap places. This becomes a minus 5 and a minus 1, which of course is just this matrix. Now to find A, I just multiply this by itself. To give 9 plus 5, 14, minus 15, minus 10, minus 25. Second row, minus 3, minus 2, minus 5. And finally, 5 plus 4 is a 9. And there we go. Hopefully now that has been enough for you to have a go at the remaining questions in exercise 5C for determinants, 5D for inverses, and the chapter 5 review exercise for all the work so far on matrices, which will continue into chapter 6. Maybe I'll see you there.